Hi guys, welcome back. Today we will take a look at analog to digital conversion, and today we will see how the ADC module works in nRF devices. So in nRF devices we have this SAADC, which is basically successive approximation analog to digital converter. It is quite common to interface analog peripherals to a microcontroller. There are a lot of devices that produce analog output, and analog output is basically a varying voltage level. So we have to read that level, and we store it in the form of a binary digital value. So what is an ADC? Basically, an ADC is a circuit which converts analog input value into a digital binary representation. We can simply say that a circuit which translates the analog voltage level to respective digital values in terms of numbers. And ADCs have a specific resolution in terms of bits. So the more number of bits means the higher is the resolution. More resolution means more quantization levels, and it means we have more accurate values. So basically the analog input is basically a varying voltage level, and this voltage level is then recognized in the ADC in terms of a binary value, and we read that value and we store it. So by this way we can process the values, and we can do a lot of stuff with the ADCs. A simple example would be some temperature sensors. Basically the temperature sensors are analog in nature, and their voltage output is always changing with the change in temperature. We can easily measure what's the temperature by just checking out the voltage difference in the circuit. So the internal structure of an ADC is basically a ladder structure, and in this structure we can see there are some resistors and some comparators connected with this 8 line to 3 line. So basically this 8 line are some 8 quantization levels. Each line represents a specific voltage value, and it's going to give an output in terms of bits. Okay. So basically it's a 3-bit ADC, and it converts the values into a binary form in the 3 bits. So the maximum value would be a 3-bit, which is 2 to power 3, which is going to be 8. So as you can see, each comparator is just representing a quantization level. The more the quantization levels are, the more complex circuit the circuit gets, and of course it's going to take more power. So in ADCs we basically read the analog input, and the analog input is then interpreted as a binary value. For example, if we are reading the analog voltage around here at this level, our microcontroller is just reading this as a number, and it's storing this number in its memory. There are two things that are related to ADC. So there is the first term is the sampling frequency. So the analog inputs are measured at a specific frequency, which is called the sampling frequency, and according to Nyquist's theorem, the sampling frequency should always be double as compared to the input frequency. And we can see here each binary value is assigned to the nearest possible quantization level. For example, if it's reading some value around here, what it's going to do is it will round this value off to either 2 or either 1. So this ADC does this itself, so you don't need to worry about too much details for now. These are the basics of ADC. So how we can reconstruct the signal if we are reading the ADC values, and these are the continuous values, but they are rather discrete sampled values. So how we can reconstruct this signal back into the original signal like this? So for that we normally use DAC, which is digital to analog converter, which gives the output in terms of discrete values, and we just simply attach a simple capacitor which smooths these curves. So the signal is reconstructed, and it's approximately equal to the original signal. And the more quantization levels there are, the more accurate will be the output signal, or the more accurate will be the input if there are more quantization levels in ADC. The NRF devices use SAADC, which is successive approximation analog to digital converter. It's a sort of a small circuit as compared to simple ADCs, and it consumes less power. We can easily integrate it in a microcontroller, and we can use this successive approximation analog to digital converter, the low power features. The digital pins that we used in our NRF devices can be allocated to any pin, any output pin, but in terms when it comes to ADC, we have to see some specific pins, and we will see what pins are there for us to communicate with the ADC module. This is the basic internal structure of the ADC module for NRF devices, and so this ADC can work in 3 modes. One is the single channel input mode, second is a double channel with differential mode, and the third one is continuous mode. And don't confuse yourself with the channels pin inputs and the channel numbers. So we will see how we can allocate these channels to pins, and we will see all the modes in which this ADC works. And we will also see how we can use the DMA, which is a direct memory access. So DMA is an important part. So basically the ADC module is very slow as compared to the processor. So if the processor is continuously looking at the ADC module waiting for the conversion to be completed, it's going to take a lot of time. So for the processor it's really slow, but in terms of simple time it's just 10 microseconds, and depends on the sampling as well, like we are doing multiple samples or we are just taking a single sample. So we can easily use DMA. So the DMA basically takes the ADC data and copies it to the memory without the processor's intervention. So the processor can be working on something else, and we can easily read the values, and once the values are stored in the memory, we can just create an interrupt, and that interrupt will be called as soon as the DMA transfer process is finished. So we will see how we can use the DMA with the ADC as well in the future tutorials. If we are using 2 channels input, then we will be using ADC in differential mode, and if we are just using 1 channel, for example the positive channel, the P channel, we are not using the negative channel. So what happens is this channel is internally grounded, so we don't have to worry about this, and we can just easily read the voltage level on the pin. And here are the pin assignments, so be sure you don't change the pins, otherwise you are not going to see the results. And so the pins are for nRF52832 and nRF52840 are similar. So the pin 0, port 0.02 means the pin 2 in nRF52832, and of course in nRF52840 we have 2 ports, P0 and P1, so be sure you are connecting with the port 0. So the analog input 0 is connected to port 0.02, and for example if we want to read the analog input value on pin number 4, then we will configure the analog input 2. So we will see how we can do this in the coding. So I think so for the basics this is enough, and let's see how we can do this in the coding. And in the coding I will show how we can convert the value into a binary, and then finally we can use some calculations to convert that value back into the voltage level, so we can easily show it to our users what voltage value we read through the ADC channel. Okay guys, now we will create a new project, and we will start coding, and we will see how to configure the ADC and simply read some input value. So right now in my case I have the development board, and on this development board there is a potentiometer, which is basically a variable resistor, and I can easily change its value by rotating it. So let's see how we can read that ADC input value. So first of all we are just going to create a new project. So go into my PC, and then in the C directory. So here we have extracted over nRF SDK, so go into the SDK and go into the examples, and today we are just going to copy of example. So go in the peripheral, and here we are going to copy this SAADC, which is successive approximation ADC. So I'm just going to copy it into my projects folder, paste it here, and just double click on it and open it, and go into the PCA 10040 if you are using nRF5 2832, and go into PCA 10056 if you are using nRF5 2840. So I'm just going to go in the PCA 10040, go into the blank, open SES, and open the EM project file. Let me zoom in a little so you can easily check. So first of all, I'm going to remove some extra stuff. Okay, so I have removed all of the code, so it's easy for you guys to see how to program it from scratch. So it would be easy for you, and keep in mind we have to do some configurations for adding it to our project. So first of all, make sure you have these libraries with you. So make sure you have this library with you, nRF5 SDK, and it's added here as well, it's included, so be sure you have this. Okay, the second thing is we need to see if the configurations are already there. So basically in this example they are already there, but if you want to use some other example, or you are using some other code, then you need to see if everything is organized as in this example. So let's see if CMSIS configuration wizard, we open this. If you don't really know how I have added this CMSIS configuration wizard, be sure to check my tutorial on CMSIS configuration. So here in the nRF5 drivers, you can see I have enabled, it's already enabled. So make sure this driver is enabled so you can use it in your code. Okay, so CMSIS configuration wizard is there. So if you want to zoom in or zoom out, just press the control button, and then scroll with your mouse to zoom in, and scroll back to zoom out a little. So I'm just gonna zoom in so that you can easily see the code. Second thing is I have these colorful outputs. So how did I change this? So just go into the tools, go into the options, and come here in the color schemes, and here you can see I have changed the things here. So if let's see, literals are basically these texts. So if I change the color from here, for example, I'm going to change it to this color and click on OK, you can see the color is changed. So you can change this color according to your needs, or whatever way you like, you can change it easily. So I'm just going to change it back, click on OK, and this is done. Okay, so let's start our coding. First of all, we need to create a simple function which is going to initialize everything for us. So we will just call it in the main function then. So I'm just going to create a new function, and then create a error code variable. You can create it either unsigned integer 32, or you can also create it by using this ret code _t, whichever you like. They are basically the same. Okay, the next thing is, so we are just going to configure our channel. So we have to tell our device which channel we are going to configure, and then it's going to turn that channel on. So it's going to read our analog values on that specific channel. So make sure you see the list that I previously mentioned, in which I have shown the pins which are connected with some specific channels. Make sure you are just connecting with the right pin, otherwise you won't see the result. So I'm just going to create a simple channel configuration. So let's call it channel config, and I'm just going to give it a default, and I'm just going to use a single-ended. So we have basically two modes. One is the differential, which uses two input channels, and one is the single-ended. So as I have mentioned previously, so we are just going to use this, we are going to see both of them today. And first of all, let's see the single-ended. So I'm just going to configure my channel, default channel for single-ended, and here I'm just going to mention the pin. and the pin has a specific constant name, and we are just going to call that specific constant name, which is nRF SADC input. And here I'm just going to mention A2, which is connected with P0.04. So if you are using any other pin, make sure you mention that pin here, otherwise you are not going to see the input results. So the next thing is we need to initialize the ADC, and to initialize it we have to give it a callback function, which is basically the interrupt handler. And right now this interrupt handler won't be called because we are not using it in non-blocking mode. We are using the blocking mode, which is going to be simply waiting mode, and in the blocking mode the processor is continuously waiting for the output from ADC. And it's not really efficient, but for normal cases we can use it. We have a non-blocking mode as well. Later on we will see how we can configure that as well, but for simple task the blocking mode is easy to implement. So right now I'm just going to create an interrupt handler for this. So basically this is an empty handler, so we are not going to use this because we cannot pass a null value, so we have to pass some handler name, and we have to create that function. Okay, now we are ready to initialize it. So to initialize that we need this error code. So once we are going to initialize it, if some error occurs during that, it's going to save that in this error code, and the error code can be checked so we can get to the errors easily. Just make sure you just enter the name of the handler and just pass it the null value for now. Okay, the last thing we are going to do in the initialization is we have to initialize a channel as well. Just don't confuse yourself with the pins and the channels. Right now the channels are basically the medium and the pins are the connections. So we can use any medium from internally, and for external we need the input pins. We have to initialize a channel which is going to be allotted to this A2. And here I mentioned the channel number, which is for now 0 to 7. The channels are from 0 to 7, so I'm just going to mention the channel 0, and I have to pass it the channel configuration values, which are basically these configurations. These are default configurations. If you are interested in seeing what are these configuration, if you just put your mouse here, you can see all of these values. And if you want to know more about it, just right click on it, go to the definition, and here you can see these are the default configurations for this. For example, we have the positive resistor disabled, for negative resistor disabled. If you are more interested in this stuff, you can just check it out, and you can see here we have the acquisition time as 10 microsecond, and the reference is internal because we are just using one pin, so the internal there voltage reference is connected with this, and we have some other stuff as well. So you can just check it out if you're really curious about what's inside the default channel configurations. So right now I'm just going to pass this channel config value, so, and then simply call the app error check. Okay guys, we are done with this ADC configurations, so let's take a look again so you can easily see what's going on. So first of all, simply we have created an empty handler because we cannot pass the null value, so we have created an empty handler for the initialization, and we just created an error code, and then we created a configuration value, initialized our ADC, and then we have initialized our channel. It's so basic right now. And the second thing we need to do is we have to initialize the log. Let's create a simple log initialization function. So if you don't really know what these log for initialization functions are doing here, just check out my logger tutorial, and you will know what it's doing here. So basically I'm initializing this logger because I want to see my values on the UOutput. So to initialize everything, let me see if the UOutput is configured. So just go into CMSIS configuration wizard. Here in the nRF log, if we click on this, and we can see nRF log UOut is enabled. So the log is enabled, and make sure you change one setting for this to see the log output. Otherwise you are not going to see it unless you are using some sleep functions. So normally I'm not using sleep functions in these tutorials. We will see how we can use those functions for the low power configurations. So for now, just click on the log nRF log deferred, and just disable this nRF log deferred. Okay, so it's going to print out the values. Otherwise, if you don't do this setting, the logger is not going to show you the output. Okay, now we simply need to call these two functions. So first of all, I'm going to initialize the log, so I'm just going to call this log init function, which is basically initializing the log. The second thing we need to do is we will initialize the ADC. So we initialize the ADC by just calling this function. The ADC is initialized. Right now we have to save the value. So I forgot to mention one thing, that we are using the ADC, and we have a specific resolution, and right now by default the resolution is set to 10 bits. We can change this resolution, we will see it later on. So for now, just let's see how we can read this value. To read the value, we're just going to create a variable from this structure. I have named it as ADC value. So let's the ADC is initialized, logger is initialized. So first of all, let's print some message. Okay, now we are just going to read the ADC value after a specific delay. We need to call a function which is going to take a sample and then convert it into a specific value. The sample read is in 2's complement, so it's just going to automatically convert it for us. And we need to use this function, which is nRF SAADC sample convert. And here we need to mention the channel. So right now we are using the channel 0. You can use a specific constant for this, like on the here you can define that specific constant and assign it value 0. That will look a little better than this, and not just simply using a 0 here like I did here. And we need to pass the variable address, so I'm just going to pass that variable that we created, ADC val. Okay, so now the value is saved in this. So now we have to show this value, so I'm just going to use a logger to show this, and we simply use the similar features as printf. So this %d sign is just going to place a variable, make sure it's integer. So I'm just going to call this variable, so it's basically a 16-bit integer value, and our resolution is 10 bits for now. To show the floating point values, we need to use some special markers from nRF logger. So I'm just going to call that function so you can see how it works. nRF log info, and here I'm just going to tell how the volts are measured. I'm going to place a specific marker here, so it's going to put the floating value here. So I'm putting the marker, so this marker is nRF log, and then we use the escape sequence, which is return carriage and then return the line. And now we are going to put that floating point value. So for that we will call another function, which is nRF log float, and here we mention that value. So the value which we read, we need to convert it into the voltage level. So for that we have this formula. So basically what's happening is we are gaining 0.3 volts, so the input voltage level is 3.3, and the gain is 0.3 volts, so it's total 3.6 volts. We will divide it by 1024. So the 1024 is a 10-bit resolution, which is 2 to power 10, so it gives us 1024. So if you are using 12 bits, this is going to be 4096, and if you are using 8 bits, it's just going to be 256. So it depends on how much quantization levels you are using, so we just change this value according to that. So now our voltage are calculated, our simple input value is read, and we need to give some delay so we can read the value after a specific delay. So in this case I'm giving it 500 milliseconds for now. Okay guys, this code is finished now, and let's see how it works. So I'm just going to build this code. Okay, the code is built, and now let's see how it works. Okay, make sure your device is connected, and make sure the serial port is also connected with your computer so you can see the results. So just go into the target, click on the connect, erase all, and then click on the target and download. And once it's downloaded, I'm just going to open this serial terminal, which is PuTTY, and click on the serial, and let's see which COM port is connected with my device. So I'm just going to go here, right click on this PC and go into the properties, and in the device manager I'm seeing this USB serial 3 CI340 COM6. So my device is connected with the COM6 now. So I'm just going to enter COM6 here, and the baud rate is 115200, and open this port. So as you can see, once I open this port, it's showing some voltage value, and I'm just going to reset it. So you can see the application started. So it's giving some voltage value, and it's reading sampled value. This is the sampled value in the form of a binary number, and it's a digital form of the analog voltage, and then after conversion with the formula, we are just seeing the output voltage. So I'm just going to use a screwdriver to change the resistance from this tiny potentiometer. So as you can see, I'm increasing, I'm moving, rotating it this side, and it's showing these voltage values. And if I rotate it anti-clockwise, you can see the voltage value is dropping. So it's reading this ADC value as 0.96 volts for now. And here you can see we can read different types of voltage, input voltage values, and then we can perform some calculation on them to read the final value. And we can use the ADCs for many different stuff. Okay guys, let's see how we can use the differential mode. So in that we use 2 pins as the input configuration. So first of all we need to change this, so let's change it. And I'm just going to select differential this time. Last time we saw the single-ended, and this time we are going to see how differential works. For differential we can use 2 input pins, and we can read their values. For now I'm just going to use one single input pin, and the other input would be the voltage level, where this will be connected internally. So I'm just going to call that. So input VDD is basically the internal value of the voltage, and I'm just connecting on the first channel, I'm connecting that, and on the second channel I'm just going to connect the same pin. I have added an internal connection. Here you can use another pin, which could be A in 1 or A in 2 or any other pin, and then we will read those two pins input, and we will assign them with a channel so that ADC can read that, and then it's going to perform some stuff for us. So for now I'm just going to connect an internal voltage level, which is the 3 volts, and this callback handler is same, and initialization and even channel is going to be same, where I'm just going to load this channel, and everything is going to remain the same. We just need to change this function here for right now, because we are using the other channel, and in that channel we have some voltage value, so this is going to be half of the total. So now this is not for 1024 but it's going to be 512. I'm just going to save it, and then click on the target, click on the connect, and build it fast, and then connect, and erase all, and download it. And now if we see, we can read this value, and I can change it, and I can see these values as well. So basically the differential, there is a little difference between them. So if you're interested in working with the differential ADC, you can check it out. And single-ended is recommended for the new beginners, and if you are already good with ADCs, just go with the differentials, because they give you some other stuff as well. For more information, you can check out the differential inputs for the ADCs and so on. For the ADCs, for now I think so you have learned a lot of stuff in this ADC. Just go and play around with the ADC module and learn more about it, and it's going to be really, I think so for now it's enough. And in the next tutorial we will see how we can configure the events, and how we can use some timers to continuously take the samples, use some buffers and so on. Make sure you download this code. I will put this code and some functions with their information, so be sure to download that as well, and play with this code, and try to read some ADC values, and make sure you don't connect high voltages. For now just connect 3.3 volts, which is the maximum for this for now. Later on in the last tutorial for the ADCs, I will show you how we can measure big batteries voltages and other stuff as well. So be sure to subscribe to my channel, and hit the bell icon to get the notifications on time. If you like this video, hit the like button, and thank you very much for watching. See you in the next video.